In the Beginning by Dr. Walt Brown. We are going to take a look at strata here on page 129 of In the Beginning. Rapid cooling on page 49. What then generated geothermal heat, and why does it still vary so much? Okay, that was from before. Strata. Earth's crust is frequently stratified with layered rock or strata composed of cemented sediments. These layers are typically parallel, thin, uniform in thickness, vast in area, and within mountains or under valleys tipped at all angles. Often one layer rests on another, having a completely different texture, color, and mineral content. What global process sorted and cemented these sediments? Present processes do not. Why are strata so uniform in hardness? If truckloads of sand and other dry sediment were dumped on your yard and bags of cement were placed in another pile, anyone would have difficulty mixing them uniformly. Without a uniform mixture of cementing agent, concrete and sedimentary rock would quickly crumble. Limestone. A typical cementing agent in sedimentary rock is calcium carbonate, commonly called limestone. Any geologist who stops to think about it should realize that based on present processes, the Earth has too much limestone. Sediments and sedimentary rock on the continents average about a mile in thickness and contain 10 to 15% limestone. How did so much limestone form? Much of it quite pure. Limestone without the impurities that normally drift in suggest rapid burial. Most limestone is in vast layers, tens of thousands of square miles in area and hundreds of feet thick. Today, limestone forms either as it precipitates out of seawater or as sea creatures manufacture shells and corals containing limestone. In either case, oceans supply limestone, the standard oceans supply limestone sediments, but oceans already contain about as much dissolved limestone as they can possibly hold. So where did all the limestone come from, especially its calcium and carbon, which are relatively rare outside of limestone? Metamorphic rock. Rocks change structurally and chemically when their temperature and or pressures exceed certain high values. The new rock is called a metamorphic rock. For example, limestone becomes marble, a metamorphic rock, when its temperature exceeds 1600 degrees Fahrenheit, and confining pressures correspond to the weight of a 23-mile-high column of rock. Diamonds, another metamorphic rock, forms under confining pressures corresponding to the weight of a 75-mile-high column of rock and 1600 degrees Fahrenheit. Yet diamonds are found in crustal rocks that were never that deep. Most metamorphic rock were formed in the presence of water, often flowing water. What accounts for the extreme temperature, pressure, and abundance of water needed to form metamorphic rock? The standard answer is that the original rock, such as limestone, was heated and compressed under a tall mountain or deep in the earth. Later, over millions of years, either the mountain eroded away or the deep rock rose to Earth's surface. It is difficult to imagine mountains 23 or 75 miles high because the world's tallest mountain, Mount Everest, is only 5.5 miles high. Raising buried layers of rock 23 or 75 miles to the Earth's surface is even more difficult to explain, but with millions of years supposedly available, few consider the problem. Most don't know the problem. Almost no one addresses it. Granite and basalt. Granite and basalt. Granite, the primary continental rock, has a grayish to pinkish color. Coarse grains of quartz, which have a glassy luster, occupy about 20% of granite's volume. Basalt, the most common rock beneath oceans today, is solidified lava, a dark, fine-grained rock. The hydroplate theory assumes that before the flood, granite was above the subterranean water and the mantle was below. As you will see, during this and after the flood, molten basalt spilled out onto the chamber floor, so most ocean floors today are paved with basalt. Plateaus. Plateaus are relatively flat regions of an extensive area that have been uplifted, not buckled, more than 500 feet relative to the surrounding regions. A plateau contains nearly horizontal rock layers. The same vertical sequence of horizontal layers surrounds the plateau, but at a lower elevation. Professor George C. Kennedy clearly explained some problems associated with lifting plateaus hundreds of feet. The problem of the uplift of large plateau areas is one which has puzzled students of the Earth's crust for a very long time. Given an Earth with salic granite continents floating on denser sematic basalt substrata, what mechanism would cause a large volume of low-standing continents to rise rapidly a mile in the air? Furthermore, evidence from gravity surveys suggests that the rocks underlying the Colorado Plateau are in isostatic balance. That is, large area is floating at its correct elevation in view of its mass and density. Recent seismic evidence confirms this in that the depth of the M discontinuity, the Moho, explained below, under the Colorado Plateau is approximately 10 kilometers, or 6 miles, greater than over most of the continental North America. Thus, appropriate roots of light rock extend into the dense substratum to account for the higher elevation of the Colorado Plateau. We have then a double-sided mystery, I believe. Double-ended mystery for the Colorado Plateau seems to have grown downward at the same time that its emerged part rose upward. This is just as startling as it would be to see a floating cork suddenly rise and float a half an inch higher in a part of water. To date, the only hypothesis to explain the upward motion of large regions like the Colorado Plateau is that of convection currents. Slowly moving convection currents in the solid rock, some 40 to 50 kilometers, 25 to 30 miles below the Earth's surface, are presumed to have swept a great volume of light rock from some unidentified place and to have deposited it underneath the Colorado Plateau. A total volume of approximately 2,500,000 cubic miles of salic rock is necessary to account for the uplift of the Colorado Plateau. While it is not hard to visualize rocks as having no great strength at the high pressures and temperatures existing at depths of 40 to 50 kilometers, it is quite another matter to visualize currents in solid rock of sufficient magnitude to bring in and deposit this quantity of light material in a relatively uniform layer underneath the entire Colorado Plateau region. The Tibetan Plateau presents a similar problem, but on a vastly larger scale. There, an area of 750,000 square miles has been uplifted from approximate sea level to a mean elevation of roughly 3 miles, and the Himalayan mountain chain bordering this region has floated upward some 5 miles. And rather late in geological time, probably within the last 20 million years. The quantity of light rock which would need to be swept underneath these plateaus by convection current to produce the effects noted would be an order of magnitude greater than that needed to uplift the Colorado Plateau. That is approximately 25 million cubic miles. Even more troublesome than the method of transporting all this light rock at shallow depths below the surface of the Earth is the problem of its source. The region from which the light rock was moved should have experienced spectacular subsidence, but no giant neighboring depressions are known. A lesser but larger problem is how such enormous quantities of light rock can be dispersed so uniformly over so large an area? The Moho and black smokers. The Mohorovičic discontinuity, usually called the Moho, is the boundary between Earth's crust and mantle. The Moho was discovered in 1909 by seismologist Andrija Mohovic. He noticed that earthquake waves traveled noticeably faster below the Moho than above. In the early 1960s, efforts were made to drill deep enough to penetrate and examine the Moho, but cost overruns and alleged mismanagement shut the project down after drilling only 601 feet into the seafloor. Today, drilling efforts are finding that above the Moho, the rock has been thoroughly fractured and is saturated with water. Free water normally cannot migrate down to those depths. What is the Moho? And why is the rock above fractured? And why does it contain liquid water? Salt dunes. Vast salt layers are sometimes buried as much as several miles below the Earth's surface. Under the Gulf of Mexico is a single salt layer called the mother salt layer. It is at least 20,000 feet below sea level, 100,000 square miles in area, and 1,000 feet thick. Many tall salt domes rise several miles above the mother salt layer. Some salt domes are taller than Mount Everest. Large salt deposits are not being laid down today, even in the Great Salt Lake. What concentrated so much deep salt? Certainly 20,000 feet of water did not evaporate. A thicker mother salt layer with dozens of salt domes is also found under the Mediterranean Sea. A co-discoverer of these deposits, using refuted arguments, claims that the Mediterranean must have evaporated 8 to 10 times to deposit so much salt. His estimate is probably low, but even so, why didn't each refilling of the Mediterranean basin redissolve the salt residue left from the prior evaporations, allowing currents to remove the basin's salt?